Okay, thank you. Can we resume recording? Oh, you've resumed.
Yes.
Now, so yesterday we looked at digital signatures. And so we've been looking at asymmetric, uh, asymmetric, how do you call it? Symmetric encryption. So I want us to look at the symmetric encryption and decryption. The symmetric one was the first one actually to have begun at the start of cryptography. So cryptography, you see, it's aimed at ensuring that communication is kept secret or safeguarded. So to safeguard that communication, what they began with was symmetric encryption and decryption. But for us, we began with the asymmetric, where we were looking at the RSA. So now we want to look at the symmetric, but I'll not begin with the modern techniques used in symmetric techniques, the modern ones. I'll begin with the traditional ones, the one they began with at the beginning of the cryptography. Now, so that is, I've said that this session will focus on traditional symmetric ciphers that were used in the past. And why are we doing that? We are doing that, I want to show you the traditional ones so that to prepare you for the modern symmetric ciphers. So first of all, you need to know the traditional ones. And then from there, now, when we advance to the modern ones, you have the basis. Now, what are the objectives that I would wish to achieve by studying these traditional symmetric key ciphers? The first one is to make you be aware of the terminologies and concepts that are to be used in symmetric key ciphers. Because we'll be looking at modern also, we shall be looking at modern symmetric key ciphers. But now the terminologies will just be the same. So that is the first objective, to ensure that we have those terminologies. And also to give categories of cryptanalysis, the attack, the one that we talked about, attacking, if you want to attack some codes. So we shall give those categories of those types of attacks. That is the other objective. And the other objective is to introduce the concept of stream ciphers. And you know, the stream ciphers, we shall also be talking about it when we're looking at the modern, when you look at the modern symmetric key ciphers, you'll be talking about the stream ciphers and the block ciphers. So then they are introduced by studying the traditional symmetric ciphers. So that is how they're introduced. Now, so we've already said one of the reasons of studying these traditional ones, and note that these traditional ones are not used presently, but we want to study them so that we get the background for the modern symmetric ciphers. And the definitions that we shall be learning in these traditional ones will be the same definitions in the modern ciphers. Now, what are the advantages of studying this? And we are saying that the first advantage is that they are simpler. These traditional ones are simpler to understand. And therefore, if anybody is a beginner, you can easily understand the knowledge of or the notion of ciphers and the knowledge of encryption, the knowledge of decryption, so that you have a background as you proceed to the modern ones. Then they give basic foundation of cryptography. That I've already talked about that. Now, so again, a look at these traditional ciphers will help you to understand that there is attacking of cryptographic systems. And also by understanding this, we'll now know why attacking has been very important to ensure that there's modern way of doing things, safeguarding information and so on. It's this cryptanalysis or the attacking of the codes that has assisted so that every time people are thinking of how can we prevent our codes from being attacked. And so they come up with the modern ways of preventing that. So again, by studying this, we hope that we can also come up with ways of trying to safeguard, the modern ways of trying to safeguard information. Now, so I already indicated that the traditional ones, the traditional ciphers are no longer used. And traditionally, they were used only to safeguard communication. But what we safeguard currently is not only communication, we safeguard a lot of things. In the modern cryptography, we safeguard, apart from communication, we also want to safeguard some activities like finance, activities like voting and so on. And so these activities, all these activities require a lot of security. And that is why it becomes very necessary to have the modern technologies of preventing attack and so on. The traditional ones are easier to attack. Those ones are easier to attack. And as we shall be going through the examples, you see how easy the traditional ciphers were, how easy it was to attack those traditional ciphers. And then as we proceed, the modern ones, you'll see how difficult it is to attack them. So I hope that by the end of this course and this chapter, you'll be able to use modern cryptography in the real world to defend things that we care about, things such as Bitcoin, cryptographic voting, and so on. So at the end of this, as we go through all these examples and so on, we hope that at the end of it, you'll be able to safeguard the information, voting and all those things that require safeguard. Now, so what is this symmetric encryption? Now, suppose I was to send you messages via communication channel, and supposing there is an intruder, and let's call this intruder Eve, and Eve has access to our channel. So that means she can see the communication between the two of us. She can see it. So the thing is, the two of us are supposed to ensure that although she sees this communication, she's unable to tamper with it. So as a sender, I want to ensure that as I send my message to you, what we call the plain text, as I send it to you, I want to ensure that although Eve sees it, although Eve sees this, the message coming to you will not be tampered with. And also you as a receiver, you also have the same hope that you will know that as we communicate, we have a lot of adversaries. So many people are trying to find out what we are communicating. But we hope that the communication you receive will be the one I send. So both of us, we are very much concerned about integrity of the communication between us. You want to ensure that what you receive, you are receiving. Let's talk about, for example, if it's voting. We want to ensure that the votes being transmitted, for example, from a polling station to the other place, are the exact votes. And so, and even the person on the other end, the person on the other end wants to ensure that what was transmitted at the far end is what is being received. So the integrity of communication is very important. And that is why we then have to see how to safeguard that kind of information. Now, so why do you call it symmetric? Why do you call it symmetric? We've said that in this symmetric, unlike the one we saw earlier, we have a key. There's just one key in the symmetric encryption. I, the sender, have one key to safeguard information, and you, the receiver, you also have the same key. The key that I have is what you have. So I'll be using it to decrypt. I use that key to encrypt, and you use it to decrypt. So it's just the same key. So we'll be using one key in symmetric encryption for symmetric encryption and symmetric decryption. For the asymmetric that we saw, for example, the case of the RSA, you see RSA is asymmetric, not symmetric. This one, for symmetric, there are two keys. There are two different keys. So the sender has, there's this public key, which I'll be using for the RSA, which is asymmetric. There's a public key, and the public key is the one that is used to encrypt communication. And then the sender is left, the receiver. The receiver, the one who generated the public key is the receiver of the communication. He remains with a secret key, a private key, that he then uses to decrypt. And the other person has the public key that he uses to encrypt. So for the asymmetric, there are two keys. But for the symmetric, it's just one key. It's just one key that the send of the message and the receive of the message have. Now, so the only difference is that, you see, for the RSA, which is asymmetric, what we said, this one key, you can use it even if you're communicating with several other people to decrypt the information. And that public, you see, there are two keys. There's a public key and there's a private key. So this public key can be used by anybody who wants to send to you information. And then you'll be using this same private key to decrypt the information they send to you. That is for the symmetric. But now for the symmetric, if I was to communicate to Alex, there is one key between us. I and Alex, we have one key. If I was to communicate to Wanjiru, I must have another key, different from the one I have with Alex. So again, this one key I'll just be using with Wanjiru. So if I want to now communicate with Cheng, again, we create another key. That is for the symmetric. So the symmetric, every communication has every two people have a different key for encrypting and decrypting. Now, so let's just as a way of defining terminologies, if I were to send you, no, if you were to send me some text, the text you want to send me is called plain text. We had already defined this. That's the text you want to send me, the original text. So now that original text, you encrypt it. Once you encrypt it, it's called ciphertext or an encryption. So you had the original key, the original message, which we call the plain text. And this plain text is then encrypted. And then once you encrypt it, we call it a ciphertext or an encryption. Now, once I receive this, I want to get the plain text. So I restore the plain text. And that process of restoring the plain text from the ciphertext is what we call decryption. And we had already looked at these terminologies. The only different thing here is that in this case, the encryption key and the decryption key will be the same for this symmetric. Now, so the other definition here, I'm now defining the encryption algorithm and then the decryption algorithm. And I've said that an encryption algorithm that now this is the algorithm that you input the plain text. Then after inputting the plain text, what comes out is the ciphertext. And then the decryption one, I'll be inputting the ciphertext. And then what comes out is the plain text. But if it's wrong, if it gives me this, then it indicates that that is an invalid ciphertext. So it's either giving me the plain text, or it can give me a special symbol. And if it gives me this special symbol, then that is an indication that the ciphertext that is there is invalid. Now, so I just want to go to the examples, but before examples, just emphasize, I've emphasized, note here that the symmetric key encipherment uses the same key. We've already said that for both encryption and decryption. And so that what that means is that if person A and B are communicating, then these two people have one key to communicate. If person A wants to communicate to person C, as I've already said, then again, they'll have another key between these two. So that means if we have M people, then we have several keys. And this is corrected by the modern encryption symmetric in ciphers. So the symmetric ciphers come up with a way of ensuring that we do not have so many keys among so many people. So this is an issue that is corrected by the modern encryption and decryption. That is one issue that we should be correcting. And the other issue that we'll be correcting is now the issue of sharing those keys. Because you remember that traditionally, sharing of those keys was a problem because I had to arrange a meeting with you. For example, if it's you, I want to give you a message. If I want the two of us to be communicating, then I must arrange a meeting between the two of us so that we share the key. Or maybe I send you over some email and the intruder may see that key. But the modern ciphers, symmetric ciphers, have a way, and we'll be looking at the way they share their keys. And they do that again. We shall be applying the same knowledge you applied last time, the knowledge of the remainders and so on. Just the same way we did for the RSA, the same calculations are used. Now, so the issue of confidentiality is very important. When you are sending message or when you are receiving, you want to be confident that the message you receive is the one that was sent and that the message you are sending will be received and tampered with. So that is one issue that is very key for these traditional ciphers. Now, so let's look what the types of traditional ciphers. We have the substitution ciphers, and then we have the translation ciphers. But we begin first of all with the substitution ciphers. And what does substitution ciphers mean? In substitution ciphers, each character or symbol or group of characters will be replaced. So I'm talking about encryption. So we want to begin now encrypting. You have some message and you are using substitution ciphers. So in substitution cipher, what happens is the character or the let me talk of if there were alphabets. Those are the ones I'm referring to, characters. It could be alphabets or digits. It could be in groups, or it could just be one. So you're saying that each of them will be replaced by a different character according to some fixed rules. For instance, if the symbol in the plain text are alphabetic characters, one can replace C with the M, and T can be replaced by a K, but you see there are rules. So we'll be looking at those rules as we look through the examples. And they could also be digits. The characters will be digits. So if there are digits, you can also, the rule can say, let's replace 2 with a 6 or replace a 3 with an 8. So those rules are the ones we'll be looking at shortly. So there are two categories of these substitution ciphers. We have monoalphabetic ciphers and polyalphabetic ciphers. And then the monoalphabetic ciphers, how do you tell that this is a monoalphabetic cipher? In a monoalphabetic cipher, if the algorithm says that letter B in the plain text should be changed to letter D, then every B in that plain text will be changed to D. Every B. Now, this is now different for polyalphabetic ciphers, but for monoalphabetic, you realize that if B is going to, suppose you have the word like book, you have a word like book, which has 2 O's. And maybe the rule says that O should go to R. So we expect every O to be changed with R, to be replaced by R. But in some other ciphers, you'll discover that you can have the word book, maybe B goes to C, and maybe O goes to something. The first O maybe goes to M, and the second O goes to J, maybe K goes to F. So this is not monoalphabetic. Monoalphabetic, if you have 2 similar characters, those 2 similar characters are mapped to the same character. Just like the example I have here, want to see whether this is monoalphabetic. Consider the following examples of the plain text with their corresponding ciphertext. So the plain text is this, and then conversion took place. Encryption was done. After encryption, this is what the ciphertext came out. We want to see whether this is monoalphabetic. So H has been replaced by W, E has been replaced by T, L has been replaced by A, and the other L also replaced by A. So this is monoalphabetic because where we have similar characters that have been mapped to the same element. But look what this other one. We have LL, 2L here. One has been replaced by N. The other one has been replaced by Z. So this is not monoalphabetic. Now, so the examples of monoalphabetic, and this is the first example we are looking at, is the shift cipher. The shift cipher is the first example we're looking at for monoalphabetic. and it's also called it is also called the Caesar cipher or the additive cipher. You can call it either Caesar or additive cipher. Now, how do we encrypt? How do we encrypt? And that's what I'm saying here. Supposing we are given these elements, these characters, we replace them by numbers. We replace them by numbers, and this is how we replace. A goes to 0, B is replaced by a 1, C is replaced by a 2, D is replaced by a 3, and all this way up to Z being replaced by 25. For instance, if we are told to add F plus G, if I was to add F plus G, what do I get? I'll first of all note what F is and then what G is. Now, coming here on this table, I can see that F is 5 and G is 6. So this is the same as 5 plus 6, which gives me 11, but then 11 is L. 11 is L. So that means F plus G is L. So this is what we'll be doing in a shift cipher. So we can add those elements that way. But what we know is that we are mapping A. M is mapped to 0, but B is mapped to 1 all the way until Z is mapped to 25. So we encrypt the message by adding a key to each letter. That's what we call encryption. We encrypt a message by adding a key to each letter and then using modular arithmetic, which we learned. So that supposing the word is MI, and we've been given the key to be K. So the key is just one element. You choose one element from between 0 and 25. So you choose one element here to be the key. So the question maybe will tell you, if you want to encrypt, so you agree with the recipient of the message, the key that you're supposed to use, and that key you make it secret. So that key, then you send it. The recipient of the message must have it. So if you encrypted by adding 3, the recipient of the message will obtain back the message by subtracting 3. If you encrypted by adding 7, the recipient of the message will decrypt by subtracting 7 from the message to get the original message. So this 3 or 7 is the key. So the person sending the message may encrypt by adding 7 and mod 25, mod n, where n is the number of elements here. These are 26 elements, actually. They're 26. Now, so I just want us to look at an example. And then decrypting just said that if encryption was done by adding K, you decrypt by subtracting K from the ciphertext to get back the original message. And this person took the original message and added K to get the ciphertext. So this is the process of encryption, and this is the process of decryption. So the first example, you agree with your friend to use shift cipher with the key D, this key, K is equals to D. Okay, let me just say D is 3. Using the key K is equals to 3. So you want to encrypt the message, Cyprian Sakwa is here. This is the message you want to encrypt. How do you encrypt this message? You go back to this table. Go back to this table. Where's the table? And change every letter to its corresponding number. What we have is Cyprian Sakwa is here. So C, you replace it by 2. Then Y, replace by 24. So you replace all the letters to numbers before you add the key. So in this question, the key is 3. So this key, as we've already said, and let me repeat, this key, the receiver of the message has it. This is symmetric. And there is the sender of the message also has it. So the sender of the message would add 3 as the key. And then the receiver of the message would just subtract 3. So this is the message, Cyprian Sakwa is here. So we change the letters to the numbers. C is 2, Y is 24, and then P is 15 all the way up to E is 4. Then add the key. Add the key. Mod 26, because those numbers, the alphabets, are 0 to 26. 0 to 26, so mod 26. So that means 2 plus 3 will be 5. 24 plus 3 will be 27, but it's 27 mod 26, which is 1. So the remainder is 1. That's what we write here. This will be 18. This will be 20. It's less than 26. This will be 11. This will be 3. The sum here will be 16. The sum here will be 21. The sum here will be 21. All the way, the sum here will be 20. The sum here will be 7. But if it goes beyond 26, as we all normally do the modular arithmetic, you write the remainder. Now, once you've added this, the key, what you get is 5, 1. Now, what is the equivalent of 5 in letters? 5 is F. 1 is B. 18 is S. 20 is U. 11 is L. This is the encrypted message that you send. This is the encrypted message. So we have encrypted this message. So when we send it, only the person who has the key, we hope, is the one who can read that message. But as we've said, these traditional ones are easy to hack, and I'll be showing you how to attack it and then be able to read this message, even without the key. You can look for this key and get it on your own. Now, so the ciphertext, therefore, is this. This is the one you sent. Now, your friend, on receiving this, since you had agreed that your key was 3, your friend knows that once he gets this message, he converts it to numbers, converts the equivalent numbers. F is 5, B is 1. Using that table, S is 18, U is 20, L, and so on. Then subtracts the key, which is 3, from each of them. Now, when you subtract 5 minus 2, 5 minus 3, what you get is 2. When you subtract 1 minus 3, this is negative 2. Mod 26. Mod 26. We normally just add this negative number plus that, and you get what? 24. Get 24. When you subtract this one, 18 minus 3, get 15. 11 minus 3 will be 8. I want where there's a smaller number again. There's nowhere else. But we know how to subtract these numbers. We know how to subtract. 1 minus 3 is -2 mod 26. We are doing it mod 26. And so that gives you 24. Now, after converting, you see the friend first of all converts these letters to the equivalent numbers, then subtracts the key. After subtracting the key, this is what the friend gets. Then finds out the equivalent letters. What letter is equivalent to 2? That is C. The letter equivalent to 24 is Y. The letter equivalent to 15 is P, and so on. The letter equivalent to 0 is A, and so on. So the friend now is able to decrypt, and this is what the friend gets, then gives it spacing, punctuation, and so on, and the friend is able to read your message. The friend is able to read your message from that. Let's look at the second example, just to emphasize. No, it's not even an example, this is an exercise. I've said use the shift cipher with the key 5 to encrypt this message. So I want to encrypt this message using this key. So I'll just use this to explain again. What you do, you convert this to corresponding numbers using the above table, where A is mapped to 0, B is mapped to 1, C is mapped to 2, D to 3, all the way up to Z is mapped to 25. So use this table to change these letters to numbers. After changing these letters to numbers, add 5 to each of those numbers. Add 5 to each of those numbers. After adding 5 to each of those numbers, now convert that result of the numbers back to letters. Convert that back to letters. What you get is the encrypted message. What you get is the encrypted message. So when your friend gets that, to decrypt, your friend does the opposite. Takes that message, converts it to numbers, subtracts 5. The result, convert to letters, then he's able to read. Now, this one I've said, use this key to decrypt this. So at your own time, just decrypt this and then tell me what this sentence is. Because it's a sentence. That means you convert this to letters, to numbers, then add 5, then convert the result to letters, and then read the text. You can now space, give it punctuation. Now look at this question. This one I'll do it. I'll want to try and do it. The question is, find the possible decryptions of this. How many English words can you form? And the way we do this is the way we can attack. This is the same as attacking this ciphertext to get the plain text. And this is the disadvantage of the traditional ciphers, because we say that the traditional ciphers are easy to attack. So you see, for instance, the numbers we are using are from 0 to 25. So you can try with the key of 1, then try key of 2, try key of 3, try key of 4. You try all the way up to 25. And when you reach 25, you check those words and see. And so you read, you're reading, you see English, that's communicating in English. After you've converted using key of 1, you check whether it's an English word, whether it's a word that makes meaning to you. And then check using key of 2, check using key of 3. So you check all the keys. You may not even go up to 25. You may have already encountered a word that makes meaning. No, I'll not do it. So let me just use it, leave it as an exercise. You try it. But what I've already explained, what you are doing is, first of all, convert this to numbers. Then try adding 1 to each of the numbers, mod 26. After you've added 1, convert the result to letters and see whether it makes meaning. If it doesn't if it doesn't form meaning, if you cannot understand what it means, then try key of 2. Now add this number, add 2. Then convert back to letters and see whether it makes meaning. So you do that until you get a word that makes meaning. And then you'll have cracked that. So I've said I'll not do that because I can see it's under this section. So I'll do one that appears here as an example, one that appears there. So I've given the types of attack on the shift ciphers. How many are they? We shall see how many. Let's say that Eve intercepted a conversation and she knows that the sender of that conversation used the shift cipher. Supposing the two of you were communicating, and then Eve gets your communication, and then she knows that the two of you, whenever you communicate, you use shift cipher. How can she break that code? So that is what we are looking at. And we are saying it's very easy. It's very easy because she has only 25 ways of doing that. She has only 25 ways of doing that. So what she'll do is what I've already explained. She'll try to assume that maybe you used, during an encryption, you used key 1, key is equals to 1. Try that and see whether what she gets makes meaning. If it doesn't, she proceeds to key is equals to 2. If it doesn't make meaning, she proceeds to key is equals to 3. And she's going all the way up to key is equals to 25. Most likely, and it's a must that one of these keys would have given, it will have given the plain text that you had sent. So that is what I'm saying here, that she has only 25 options of doing that. So she will test each of these shifts in turn. So what is this, the name of what is the name of this type of attack? Where you're trying each option. Yesterday I said that kind of attack is called brute force attack, where you are trying every option to see whether the key, did the communicator use key 1, did he use key 2? But here we have limited options. We have only 1 to 25. So this it's very easy to use this brute force attack, which we also call the exhaustive search. Some books will call it exhaustive search. So this is where you are trying every key to see whether you get meaning from decrypting. So if there are few keys, we can decrypt all of them in a very reasonable time. Suppose these are 25, for instance. We can do that in a very reasonable time. But if there are many, then it becomes, we can still do it, but it will take long. Because we are trying each of the keys. It will take long, but we can still attack and get the message you intended to send. Now let's look at this example, therefore. You intercepted this ciphertext This is a ciphertext you intercepted. Show how you can use brute force attack to break the cipher. So we want to read, we want to know what this sender wanted the receiver to read. So what we do, since we don't know the key, we try key 1, we try key 2, we try key 3, we try key 4, and so on. So we, first of all, we change these letters to numbers. So we know that we have A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, and so on. But now this one goes to 0, this one goes to 1, 2, 3, this was C. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'll not go up to the end. I only required M. I only required M, but you have to do all of them. Now, so M is what? M is 12. M is 12. M is 12. And let me, what about the next one? N. N is 13. F. Or F is 5. F is 5. G is 6. J is 9. C is 2. The next one is B. B is 1. The next one is F. F is 5. Then we have X. X should be 23. And then we have U. Did we reach U? Okay, but these are enough. These are enough just to use as an example. Now, so this is the ciphertext we've met. You meet it and you want to understand what it means. So, and you know that the person who sent this message must have used the shipped cipher. So what you then do, you'll try a key of 1, add 1 to each of these numbers. When you add 1 to M, you get 13. What is 13? 13 is N. When you add 1 to this, you get 14. What is 14? Is O. So when you do that, the plain text you get, what is that? Okay. Which one is this? So we are trying for, okay. So you try this. Oh, this is ciphertext. This is a ciphertext. We want to decrypt it. So you subtract the key of 1. So you try by, you see, we are decrypting. It was encrypted by adding. So we decrypt by subtracting. So let's suppose that the person encrypted using key of 1. So we subtract 1 from each of them. So when you subtract 1 from 12, you have 11. Just a minute, you have 11. So what is 11? 11 is L. 11 is L. Then 13 subtract 1, you get it 12. What is 12? 12 is M. And then F, G, 5 subtract 1 would be 4, and 4 is E. So we are decrypting this message. And then the next letter here is G, which is 6. Subtract 1, you have 5, but 5 is F. So this, when I did that, this is what I got. This is what I got when you decrypt using key of 1. So you look at this word and you cannot see, even if you are to try to punctuate it and so on, it cannot bring meaning. And you know that these guys were communicating in English. So most likely key of 1 was not used. Now you now proceed and try key of 2. You try 2 as the key. Let's try that. Subtract 2 from this, you have 10. You have 10. What is 10? 10 is K. Subtract 2 from this, you have 11. What is 11? 11 is L. So you have, this is what I got when you do all of them. And again, this one does not appear to be making any meaning, even with any punctuation. You cannot even tell how to punctuate this. It doesn't make meaning. So you most likely 2 was not the key. You proceed, and you have very few options. You want to do up to key of 25. So we proceed to key of 3, and this is what you get. You proceed to key of 4, this is what you get, and again, it doesn't make meaning. You proceed to key of 5. When you look at this, it appears to be making meaning. So you can try and punctuate, and you can see when you punctuate this, looks like something like, hi, Alex was present. Alex was present. So that means you're now trying to space these words because it looks like it makes meaning. And you can see where you can now space them. You can space, or if you want, you can put a comma somewhere or a full stop somewhere. So you are punctuating them on your own. This is how we can attack a shift cipher. So you try every key, you try from 1, you can try up to 5 and discover that you're not getting a word a sentence that makes sense. You try 6, try 7, try 8, and so on until you get the right key. So that is one kind of attack, and we call that one brute force attack. The other one, and I've not included an example, is the plain text attack. This is where you know part of the plain text. For example, if you know that this guy, for him, whenever he sends a message, it begins with the word hi. So you already know part of the message. You already know part of the plain text. So supposing this is what you found. You found something like this, M, N, H, K, M, and so on. Just giving an example. Supposing this is what you got. And you know that this guy, whenever he talks, whenever he writes a message, he must begin with a hi. This means this M should be H. So if M is H, you can now subtract to find out what key was used. What key was used if M is H? So you just go to the numbers. What is M? What is M on the numbers, and what is H? Let me use the example here. There's this example that I have here. So I know this guy begins with the hi. So I want to determine the key that he used. I may not say he begins with the hi there. Let me just assume he begins with the hi. So if it begins with the hi, then L goes to H. But what is L? We're using our numbers A, B, C, D, E, F, G, H, I, J, K, L. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is 11. What about H? H is 7. So what happened here? You see, this person was encrypting. So supposing this person added 4 to 7 to get 11. This person added 4. So that means this was H. So for us, we want to decrypt. So that means we now subtract 4 from each of them. Subtract 4 from each of them. See, this is K, L, M, N. So when you subtract 4 from M, what do you go to? 1, 2, 3, 4. You land to I. You land to I. When you subtract 4 from M, because M is what? K, L, M. This is 12 minus 4, that gives you 8, which is I. Now, what about this E? Let's subtract 4 from E. E is here. When you subtract 4, you land at A. What about P? Subtract 4, let's see. There is P here. Let me go back to the table and just subtract 4 from our table was somewhere here. Where was our table? Yes, P is 15. When you subtract 4, you land at 11, which is L. You land at 11, which is L. So let's go back to the question. So you land at L. And then there's this I. Let's subtract 4. Let's subtract 4 from I. I is 8. Subtract 4. You go to 4, which is E. And then there is this B. B, subtract 4. So what you're saying is 1 minus 4. Remember, it's mod 26. This is negative 3 mod 26, which is 23. So the letter is number 23, which is X. So this is, hi, Alex. How was I able to decrypt this? I was able to decrypt this because I know that the send of this message always begins with the hi. So that means I have part of the plain text. I know there's a H, the first letter is a H. So using this H, using H and this L, I can get what the key that was used is. So this kind of attack is called plain text, non-plain text attack. Non-plain text attack. So non-plain text attack does not mean that you know the whole plain text. You may just be knowing a part of it. You may be knowing how he begins the message or how he ends his messages or something in between. You have an idea what the send of this message does, something in between. There's another type that we call the frequency analysis attack. The frequency analysis attack is used mostly where we have large ciphertext. Where you have large ciphertext. So you're looking at the numbers that appear more, the letters that appear more, the frequencies of letters. So you know, in the English alphabet, when you're writing words, there are numbers which appear more in the words. For instance, let's just check from here up to here. you realize that these sentences, there's no Z somewhere. There's no Z. So Z appears less number of times. And when you check, you discover that we have letters which appear more. Like E. If I was to check E from just where I've marked to this end, you discover that E is appearing the most number of times. So the frequency of E appearing is very high. So that is what we call the frequency analysis. That is, you're given, for example, I'm given this sentence, and you're given a very long text, H, F, G, M, G, K, G, N, G, and it's a very long sentence. So you now go through this sentence, this long sentence, and check which is the most letter that is appearing many number of times. And from here, I can see that G is appearing very many number of times. And then you go to the frequency table. The English frequency table gives E as the number, is the letter that appears the most. So it means this was a ciphertext. This was a ciphertext that you made, and you're looking at it, and it was a very long one. It's a very long one. It must be very long. And then you're looking at it, you're seeing that there are letters that are appearing more than others. There's one that is appearing only once. There's one that is appearing only once, and others appearing more number of times. The one that is appearing only once could be even a Z or something else, because a Z appears the minimal number of times. But the one that is appearing more is likely, I'm not saying for sure that it's an E, but it's likely to be an E, because this is a method you're just trying to guess. You're just trying to guess. Just trying to guess. So you say this is likely to be an E. This ciphertext, this number that is appearing, this letter that is appearing more number of times is likely to be an E. So now, if you settle to an E, then you can use that to try and get, you see that G now goes to E. If G goes to E, then you can find what the key is. For instance, what does E represent in terms of numbers? What does G represent in terms of numbers? What does E represent in terms of numbers? Then get the difference. That difference is the key. Apply that key to each of those letters now. Apply that key to each of those letters and check whether it forms meaning. The chances are that it will form meaning, it will make meaning. Chances are. In some cases, it may not. So if it's not, then it means that this G is not E. Then you go to the next number, the next letter that is that appears more number of times in sentences. You may now even want to choose an A. You may say that this G is A, or maybe it's a T, or maybe it's a T. So you're just trying, you try this, and you'll discover that at the end of all those trials, you will get the one key that was used. So this type of attack is what we call the frequency analysis attack, where you are using the frequency of appearance of letters in the English words. So that's why I would say the frequency analysis attack involves looking at how many times each letter appears. And sometimes it could even be block of letters, For instance, you would find something like every time M appears, there's a G. And every time M appears, again, there's a G. So if that is the case, then I know that there are some letters that follow each other that way. For instance, Q is always followed by a U. Q is followed by a U. So you can see, so you can now say, if this is the case, because I'm seeing every time in this sentence I've been given, every time an M appears, there's a G. Every time an M appears, there's a G. So then I say that M could be Q. Use this, convert this to number, find the key, the difference, find the key. And then also try if there's the same thing. Supposing that Q is M. What about, supposing that M is Q, what about G? So you're saying that this G is likely to be U. Find out again if this key you found here is the same key here. If that is the case, apply it uniformly to all the numbers, all the letters. So what I mean is, when you're using this frequency analysis, you look at the letter that is appearing more frequently. And apart from that, you also look at if there are block of letters, that are appearing together. Every time they appear together. Those block of letters, they can also assist you to come up with a key to decrypt that message. Now, so the advantages of the shift ciphers are here. It's easy to implement. It requires only a small set of pre-shared information. But what is important to me again are the disadvantages, because the disadvantages then will assist us to attack it. So you're saying that it's not secure. You can use the brute force method to attack it if a small number of keys are the ones used. Is not suitable for long text. Also, you said that where there's a long text, that one you can take the shortest time to guess that this letter is, I think it's an E, or this block of letters that are appearing together every time, the Q and U and so on. So for a long text, it's easy again to attack it. So it's not suitable for long text because of that reason. Now, the other monoalphabetic cipher is the affine cipher. And again, I'll just go through the examples. But before that, what does it entail when you are encrypting and when you are decrypting? Now, the affine cipher uses an ordered pair of numbers. There's one thing that is very important here. This first number here must be relatively prime to n. Must be relatively prime to n. Relatively prime. This first number here. But this one, there's no problem. But this first number here, it must be relatively prime. So how do you encrypt a message? Using these two numbers, how do you encrypt a message? Supposing your message is X. Supposing your message is X. Multiply X by the first number, which I said should be relatively prime to N, and then add K2. So multiply your message. This is a plain text. This X is the plain text. You want to create a ciphertext. This is what you want to create. So how do you create a ciphertext if you have the plain text? The plain text, for instance, it was a sentence. If it was a sentence, convert it to numbers. Once you convert to numbers, multiply each of the numbers by K1 as you add K2 to the result, mod N. And I emphasize here, K1 is chosen such that it's relatively prime to N. So I emphasize there. Now, how do you decrypt? How do you decrypt? To To decrypt, it's unfortunate I used different numbers. This is supposed to be K2, and this is supposed to be K1. Supposed to be K2 and this one K1. So to decrypt, you just get the inverse of K1. Get the inverse of K1. Then first of all, subtract K2 from the ciphertext. Subtract K2 from the ciphertext. This one is also supposed to be, this one is supposed to be the ciphertext. So subtract K2. So in fact, let me just write it properly. Di is the inverse of K1 into the ciphertext minus B, no, K2, minus K2 mod N. I want to go to the examples straight away so that you understand what I'm saying. Now, so you with your friend, you agree to use this, a fine cipher, and this is the key that you want to use to encrypt this message. So how do you encrypt this message? I've already said, to encrypt this message, convert each of these letters to their corresponding numbers. Convert the letters to the corresponding numbers. After converting the letters to the corresponding numbers, multiply each of the number by our K1, and then add K2. So when I multiply this number by K1, I get 6. 6 plus K2, which is 5, I have 11. Then multiply this number by, remember every time you're doing that, it's mod 26. Mod 26. So your product and addition should not go beyond 26. So what is this? 28 times 3, or 24 times 3. That would be 72. 72 and then add 5. This will be 77. Mod 26. So ask yourself, if 26 were to go here, what will be the remainder? The remainder will be 25. Do this one again. 25, 15 times 3. That gives you 45. Then add 5. This gives you 50. Mod 26. So what is the remainder? 24. Then this one again. So the fine cipher tries to be a bit more secure than the shift cipher. Because for you to decrypt this affine cipher, you have to know two keys. You have to know these 3, and you have to know these 5. The two of them, you have to know both of them for you to decrypt. Otherwise, you will not. Now, do for each of them, do for each of them. Multiply by 3, then add 5. Multiply by 3, and then add 5. You get this. After getting this, get the corresponding letters. The letter corresponding to 11, the letter corresponding to 25, the letter corresponding to 24, and so on. So when you do that, you find this. So this is your encrypted message. That is the one you send to your friend. This is the encrypted message. So if your friend gets this, how does your friend then decrypt it? You already agreed. You see, you agreed with your friend to use this key. So your friend has this key. So what the friend does is the inverse of what you did. So your friend gets the inverse of 3, the inverse of 3 mod 26. Your friend will be doing this using the extended Euclid's algorithm to do that, or can even use the Euler theorem to do that. So your friend gets the inverse of 26, 3 mod the inverse of 3 mod 26, and your friend gets 9. This one, you know how to do it. It's 26, 3 goes there many times. What's the remainder? Then 3 will be going there, I think, 8 times. And the remainder will be 2. Then what about 2 into that, and so on? What about 2 into 3? 2 go there, 1. The remainder is 1. So this is the GCD. Then reverse. You find that the inverse of 3 is 9. So once you have the inverse of 3, what we said, for you to decrypt, now subtract 5 from each of these numbers. And after subtracting 5, multiply by 9, mod 26. For instance, this first one, subtract 5, you get 6. Then 6 multiplied by 9, what you get is 54. 54. And then what is 54 mod 26? 26 goes here twice, and the remainder is 2. What about the second one? Subtract 5, you get 20. That 20 multiplied by 9. The answer you get, reduce it, mod 26, you get 24. Then do for all of them, and after that, convert these numbers to letters. When you convert those numbers to letters, this is what you get. You have decrypted that message. So that is how you encrypt, and that is how you decrypt using the affine and the shift ciphers. But now, how do you break the affine cipher? Now, so we talked about how to break the other one. Now, this one, if you're to break it, how do you, supposing this Eve gets this, and you see it's using 2 keys, how will she break it? She will have to form 2 equations here. She'll have to form 2 equations and then solve them simultaneously. So she must be knowing that this affine cipher which was used. Then after she knows, she will assume that the first, let's assume that this person used AB. Let's assume this person used AB to decrypt, to encrypt this. Now get the inverse of A mod 26. And then do that, and then multiply. I think we will look at this decrypting, this breaking the fine cipher in the next class. So where I'll be looking at this example and any other example. Now, there are some questions here that you'll need to try a bit. Suppose you have intercepted this ciphertext and you didn't know what the original message was and you wished to know it. Try and see how you can decrypt that. And this one also, try and see how to decrypt it. It's okay, let me just show you the working that I used for breaking this so that you can record it and so that you can also read it slowly. This is my example. I had said the person will come up with the 2 questions. And after coming with the 2 questions, just by using elimination, you can subtract here. You can see that this is 2x is equals to 6 mod 26. So y has been eliminated. And then make x the subject of the formula. And then you'll come back and find y and so on. So you have the function that was used. But then I'll look at this example later again with another example. Thank you.
Thank you very much, Dr. Sakwa. So today's class was actually quite interesting, and for me, I'm seeing light at the end of the tunnel. So thank you, Mwalimu. So what then? 10, our
Just
sister
before this,
yes.
I can see a question by Wesonga. I had not seen it, and maybe Wesonga, next time you just raise your hand and then ask. That is when I'm now reading the text. I can see you asked when we are decrypting, do we add or subtract? Now we subtract. I guess you are talking about the affine cipher. When you are encrypting, you are adding a number, and then the person decrypting does the opposite. The person decrypting, so you added, the person now subtracts. Then somebody's here, Jeff says, can the key be a big number? For this type, we say that it's easy for us to attack. The key is just between 0 and 25. In fact, it's either 1 or 2 or 3 up to 25, because the letters are going, these letters are mapped to those numbers. The letters are mapped to those numbers. So the letters are mapped from A to Z, mapped to, that is 0 to 25. So we cannot use a very big key for this type of encryption and decryption. Thank you, Alex.
Thank you. So we have created a dedicated Math for Web3 sub-channel in the main Web3 Clubs channel. So if you look for that in the community groups, you'll find it. Also, 10 had come up with this idea and communicated it to us.